Alright, so I want to talk about indefinite integrals with trigonometric functions because this is really fun. This is a really interesting way to start looking at indefinite integrals. So before we get started, as a preliminary note and precursor to all of this, if you are unfamiliar or just a bit shaky with the differences between definite and indefinite integrals, go ahead and check out my video on that, integrals definite versus indefinite or something along those lines. It will be on this playlist on my channel, and it should clear everything up for you, hopefully. Alright, so let's go ahead and get started. As a quick review for this video, the indefinite integral is just simply asking us an integral of some function, dx, that's going to give us the antiderivative. Alright, so what does this mean? What does the antiderivative mean? Well, all it means is what function, when we take its derivative, is going to give us f of x. Something prime equals this, we just don't know what. So if this is 2x, right, then we know that what prime equals 2x? Well, we know that x squared prime equals 2x, right? Is this correct? Yes, of course it is. So that is all we're talking about. What function, when I take its derivative with respect to this variable, dx, dy, dt, whatever, is going to give me the function here within the integrand. So that is all we're talking about when we talk about indefinite integrals. When we have trig here, when we're starting to use this with trigonometric functions, things are exactly the same as when we're using just a regular polynomial or a rational function or something like that. It just becomes a little bit more interesting procedurally because we have to remember what our trig functions are really meaning. So let's go ahead and do an example here. Alright, so not a terrible difficult one to start us out. I would like to find out the indefinite integral or the antiderivative of theta minus cosecant theta times cotangent theta not dx, d theta, I'm sorry, because we're integrating with respect to theta. If we were integrating with respect to x, we certainly could, but we would have to do it. Implicitly because there's no x showing up. So, all right, what do we need to do to find this integral? There we go, d theta. So this is what we want. What do we need to do? Well, we're just saying what function, when I take its derivative, gives me this. Now, unless you are Stephen Hawking, I doubt that you can just pull out of your hat the function that, when I differentiate it with respect to theta, is going to give me this. So there's a little bit of work that needs to be done. It's really not that bad. I think the best thing we need to do is we can integrate this sum by term and then factor out constants. So what does that mean? Well, all it means is we've got an integral minus another integral. So all this is really saying is the indefinite integral of theta d theta minus the indefinite integral of cosecant theta. I'm sorry. Indefinite integral of cosecant theta cotangent theta d theta. Now let's remind ourselves here, what is cosecant? What is cosecant really? Well, cosecant is really just 1 over sine theta, right? So this is going to be helpful for us. And really, what is cotangent? Well, cotangent is cosine over sine. Cosine theta over sine theta. So, how can we rewrite these now that we know that cosecant theta is just 1 over sine theta and cotangent theta, we've recognized it is really rational itself as a cosine theta over sine theta? Well, how can we go ahead and rewrite these? Well, I think the best thing for us to do is just multiply it out. Cosine theta over sine squared theta. So this is really just the integral d theta of cosine theta sine squared theta. Okay, now don't worry, I know this is horrible looking. I'll rewrite it better on the next page. So here's what we've got going for us up to this point. We know that now we've broken all this down into the integral of theta d theta minus the integral of cosine theta over sine squared theta d theta. So let's go ahead and rewrite this on the next page. Here's what we've got up to this point. We have got the integral of theta d theta. And, you know, I'll put some brackets around this so that everything looks very separated and it's obvious what we're doing, minus the indefinite integral of cosine theta over sine squared theta. And of course, we can't forget all of this just integrated with respect to theta, so d theta. So this is our new function. This right here is exactly the same as this right here. We have just rewritten things. We haven't integrated anything yet. We've done nothing. We haven't found anything. We've just moved it around to make it a lot easier to work with. So we've recognized things for what they are. So let's go ahead and do a u substitution for the integrand. So we have two integrands here. We have the integrand of theta. We have the integrand of cosine theta over sine squared theta. So let's do a u sub. Which one of these is going to be smarter for us to u sub? Well, I personally hate rationals, and I think they're well, I love rationals, but I hate working with them right now in this type of function. So let's go ahead and do a u sub for this rational. So let's say that u is sine theta, sine squared theta, right? Oh no, better yet, let's just make u sine theta. Okay, so we'll have u equal to sine of theta. Oh, this is going to work out really cool. So if u is sine theta, then what's du? Well, du is going to be the derivative, so it's just going to be cosine theta du, or d theta, right? Because we have to use the chain rule there, so cosine theta d theta. So now that we have this cool little bit of information here, what can we do with this? Well, we can say this, we can rewrite this. We've got the indefinite integral of cosine. Why on earth did I write dt? That's stupid. It makes no sense. Okay, d theta. Wow, weird. So we have the integral of theta d theta. Okay. And we're now subtracting, and look at this, the integral of 1 over u squared du, right? So, what is this going to allow us to do? Well, it's just going to allow us to take the integral of 1 over u squared. So, if we take this information and go on to our next page, we can say that the integral of 1 over u squared, and we're just using our integral rules here, 1 over u squared du is just negative 1 over u. So because we have this bit of information on our side, we can go ahead and now rewrite. We have our integral of theta d theta plus 1 over u. Now, I said plus 1 over u. Why? Well, look, it's negative 1 over u, and we're subtracting. So right here, subtracting, negative, so this is just going to cancel out and make everything a positive. So now we have the integral of cosine, not cosine, the integral of theta d theta plus 1 over u. Now we need to go ahead and get our theta. And how are we going to figure out the integral of theta? What do we do here? Well, let's think about it this way. There's a neat little rule that we learned. Well, if you watch my other videos, you've learned it. Perhaps you haven't. So let's go over this here really quickly. If we have anything to any power, if we have x to the nth power, and we want to take the indefinite integral of x, let's rewrite this better. If we want to take the indefinite integral of x to the nth power dx, there's this neat little rule that we can use that says all we have to do is know how to add by 1. That the top, it's going to equal a rational where you have on the top x to the n plus 1, and on the bottom you just have n plus 1. So what n is just the power you raise to. You add 1 to that power, rewrite your variable, and you're good to go. So let's go ahead and let's use this neat little rule over here. And so what is theta? Well, theta is equal to theta to the first power, right? So theta to the first power, if we add 1 up here, we're just going to have theta squared over 2, right? So the integral of theta, d theta, is just theta squared over 2. So this is really useful for us because now we have that integral. So now we just need theta squared over 2. We have this information. Theta squared over 2 plus this 1 over u, right? So plus 1 over u. All right, we're done, right? No, we still have some other stuff we need to take care of first. We can't jump into this. Okay, so we did a u-sub earlier, so we always have to pay for that later on down the road, especially with indefinites. If we're doing definites, then we can fudge around and mess with the endpoints, and then we can not have to worry about resubstituting our u when we're done. But because we're doing an indefinite integral, we're always going to have to resub that u. So let's go back and see, what was our u? We said our u was sine theta, and our du is cosine theta d theta, but all of that was because we had cosecant theta times cotangent theta. So if we're going to go in and appropriately resubstitute our u, then all of this should bring us down to theta squared over 2 plus, guessed it, cosecant theta. Excellent. So we have this. And we might think we're done, but there's still one little final step we have to do, of course, when we're taking an indefinite integral, which is to add a constant on the end. So it's the final answer here is theta squared over 2 plus cosecant theta plus c. All right, so why are we adding this c? Let's talk about this really quickly. I want to talk about this every time I do it to make sure we understand why we're doing this. We're adding this c because, tell me, what is the derivative of, and because, of course, we're talking about the antiderivative, so we're saying that this function right here, when we take its derivative, we're going to get this, right? So that's the point of what we're doing. So, what is the derivative of this function? Well, we know it. We just talked about it. What is the derivative of this function if we add 7 to it? Well, it doesn't change, because 7 as a constant always goes to 0 if you differentiate it. The derivative of any constant is 0. So I know what you're thinking. What if at the end of this function we just have a 0? There we don't have anything. We have nothing added to it. It is the final answer, in all honesty and truth, is just theta squared over 2 plus cosecant theta. There is no constant. Well, no constant is the same thing as saying, and I kind of gave it away earlier unintentionally with the slip of the tongue, 0 plus 0, because if you have nothing, you can add 0 all day long, as many times as you want, and you will never change the value of that function or that expression or whatever it is that you're tacking 0 onto the end of. It doesn't mind. So this is your final answer right here, and we're done. And yeah, that's it. That's all there is to it. This wasn't a terribly challenging problem. That u-sub might have been a potential tripping roadblock, and this recognizing cosecant theta and cotangent theta as separate rational entities of 1 over sine theta and then cosine theta over sine theta for cosecant theta and cotangent theta respectively, and then being able to just multiply those rationals together into one single combined rational with square on the bottom, the sine squared theta underneath cosine theta. I think that's extremely important that there's no mess ups there, because that will screw up the entire problem. But yep, this is it, and we're good to go. That's all there is to it.